So we put the machine together. Essentially, we have a stator and a rotor and an adapter base, right? So the stator was already on the adapter base, put the rotor in, and then we had another unique idea. This is what it looks like. The air gap was about a 1/2 inch when you're done per side, so quite an air gap. So we made this steel plate, and what happened was originally we were going to use that as just for shipping. So when you ship it, you block it. So when it's going down the road on a truck, it's not going to hop around and damage things, like hit the rotor to the stator. Well, the second one was when we were thinking about this, there was a guy working with us that said, why don't we make that thing center our rotor for us? So in other words, set our air gap at the shop and use this as the piece that once we set it, we pin it and locate it, and we can quickly duplicate that on site. So we used that idea. Not only was that a sleeve for shipping, it was a sleeve for centering. Some final details, the weight of that new adapter and the shaft. Remember earlier I said the original motor, the EP motor, was 44,000 pounds. The Alice Chalmers original was 61. Well, when we added our adapter and the new shaft, we ended up being 57,000 pounds. So we were really close to the original. So the last challenge, and this again, this was another thing that kind of was stumbled upon. That's the solid state exciter. We had final plans and a date set, and then I started reviewing details. Already knew, we had already built everything. In their system, they said they had a 250 volt exciter, and I was assuming they had an amperage that was higher. Well, it was limited to 80 amps. Our new design was rated at 99 amps. So we had a moment where we were going, okay, what are we going to do with this? Fortunately, we were able to get with the solid state exciter manufacturer, Kinetics, a great company. Worked with the owner of that company. He said, this is not going to be hard. You've got the SCR or transformer ratings in the exciter right now. All you got to do is change something on the board, some fusing, and another small control transformer, and you can produce 99 amps. So for $340, within that time frame, they were able to get the parts. They happened to have a spare board that they could send, and we operated the exciter. So we were past that, and now we were back on track. But there was kind of a little bit of a scary moment because we're like, okay, we got this thing done. Your exciter isn't going to work, but we figured out how to get past that. So here we are, now ready to put the motor in. And we have to remove those three pieces, the motor being in the center, and the adjacent ones had to be removed because they're coupled to the motor. So the first generator was removed, and I believe the second generator is off there. That was the first time I saw the design of the coupling face, because from that point, we had nothing but our concept and what we calculated it to be based on the armature couplings. So I was able to get in there and measure and make myself feel good that my dimensions were right. The stator, all of this was picked up with a 100-ton portable crane that was brought in. Their crane system didn't reach this drivetrain, so they couldn't even pick them with a regular crane. We had to get a portable crane that had to reach over and pick all this stuff out. So this is what it looked like with the motor removed. And then one last thing, we had identified it earlier on, but there was still a oil line that had to be moved. Our adapter base was going to hit that pipe. So they had to get some pipe fitters in there. And it all worked out because there was timing in there that we had to set things up. And be honest, the steel mill doesn't move that fast. So not picking on them, but I mean, you know, it's a big operation and lots of things are going on. So our motor was installed in the pit. I was feeling pretty good because everything was lining up right. When we set the air gap, the piece is already off. We were able to use that device and set the air gap. Saved us, I'm getting ahead of myself, but saved us probably 6 to 8 hours of taking feeler gauges and adjusting the stator left, right, up, down to get the air gap, bolting it down to the base, setting up the brush holders to the rings, lagging it down, just different views, the air gap was predetermined, but that's what it ended up being again. And so installing the motor was really intense because it had never been in that spot yet. We had calculated and we remeasured and measured, but it was a culmination of 4 years spent on a project that tested my abilities and knowledge and everyone around me to overcome all these different challenges. Now we were ready for the next part. Will the motor, from the calculation of the rotor on the shaft and the position of the stator, am I even going to be on a magnetic center? That's why we were going to run the motor. So the motor was ran uncoupled. And what was really sweet was when it was energized, the motor synced immediately with no issues. The original motor, they would have to start like 5 different times to get it to sync. So we were feeling pretty good. And then probably what I felt the most good about was that the magnetic center was right on. It was dead on. It was right in the sweet spot between the mechanical. So we didn't have to go back because one of the steps would potentially was, after this test run, was we would have to shut down and then go back, unbolt the stator and move it in a direction to bring the rotor back this way or this way. But the calculations work. And I'll just tell you this, that doesn't always work that way. You can apply that logic and there's some other things that can play that will impact the magnetic center. And it just happened to fall in the right direction for us. So the motor was in, now we put the DC generators back in. Another critical time because this motor now had never driven that powertrain. And we had calculated inertias. So even though you feel like a confident engineer, you're still at that point going, okay, I hope all these numbers are right. And even though you had gone through them over and over and over. So the motor was put together, put in place, the guards were put in place, air, remember, is coming up from the tube, so we made these end shields to allow the air to get into the motor. And the final run, and we'll just show part of this. So I was pretty happy because it started and synced again right away. And so once we knew we were good there, they began to excite the exciters to produce DC power. And it operated really well. So I was pretty happy. Vibration levels were lower than they had ever seen. The machine was operating better than the original, and the vibration levels were almost unnoticeable. Yet we were on site with our vibration equipment, checking it out just to make sure. So that's the whole drivetrain. So the motor ran good. This is what it looked like again. So those DC generators on both sides are feeding now these cluster of DC motors, and there's some more over there that feed this mill, or this temper mill they call that, or sheet mill. So sheet metal comes through there, and then they change it to a new size. That's what this project did. That motor generator set was feeding these DC motors that operated this system, and they had 2 of them in the plant. So final summary, project spanned 4 years. The extended period of time wasn't due to us. What happened in that 4-year time frame, the customer changed 4 managers. So I dealt with the first guy. He was gone within like 3 months, and I had a new manager. I had to reintroduce everything and get everybody back on board. Then they changed that guy a year later, and it just kept getting stopped and started and stopped and started. So very frustrating from an engineering point of view. Had many twists and turns, but it was an engineering success, reverse engineering and manufacturing to overcome challenges and all those unknowns. Motor ran better than the original. The customer was extremely happy. And it saved them about $500,000. The original motor was going to cost, a new one was anywhere from $1.5 to $2 million. And we were able to save them about $500,000. Our project total was just shy of $1 million to do all this. But, the point is we saved them quite a bit of money.